Okay, so we are moving now into section 5.10, and we're going to talk about improper integrals. Improper integrals. Let me give you a moment to copy this example down, okay? Okay, so let's look carefully at this integral. It's a definite integral, but we're calling this an improper integral. Why would we be calling this integral? Why would we be calling this improper integral? That's right, Jonathan. Very good. The bottom limit is negative infinity, right? The bottom limit is negative infinity. So that's going to make this integral an improper integral. All the integrals you've seen up to now, the definite integrals, had finite limits on the bottom and the top. The left limit was finite, the right limit was a finite number. Now you have this negative infinity. So, all right. So what we have to do is we want to know if the integral converges or diverges. So if an integral converges, that means converges means the area is finite. The area between the function, and in this case, the function is x times e to the x power. Okay, that function, you'll see a picture of that function, and we want to know if the area between that function and the x-axis going from negative infinity to 0 is finite. If it is, we say the integral converges.
Professor?
If it doesn't, if the area were like infinity, or we couldn't find it, we would say the integral diverges. Yes, Cleo?
I'm sorry, but I don't know the meaning of the word finite.
Finite means like a finite number. So like infinity, this is infinity. That's not finite. But finite, well, Jonathan says something you could count. Of course, like 12 apples is finite. That's right. Could be a decimal, though, like 7.8 as well.
Oh, I see.
Measurable. That's right, Avery. That's right. Good, good. So, all right, let's take a look at the graph. So on the next page, I have a picture. I have a picture of this. And here's the function. Here it is. Okay, there's the function. And you see it goes on to infinity, goes on to negative infinity. And I'm interested in this area between the x-axis and the function. Okay, I'm interested in that area. And the area keeps accumulating. Now, the function gets closer and closer to the x-axis, but there's more and more area building up. The question is, how fast does this area build up? What's the rate at which it builds up? That's going to determine if the area is finite or not. So what we have to do is, with the techniques that you've learned, substitution approach, integration by parts, and so forth, those techniques are based off of proper integrals where you have finite limits for your integrals. So what we're going to do is, the way we compute this is we take that negative infinity on the denominator, and we replace that negative infinity with t. So you notice these two integrals here are the same integral. It's just the bottom limit, negative infinity, got replaced with t. But then what we're going to say is, okay, well, I want to take the limit of this integral here as t approaches negative infinity. And that's equivalent to then this improper integral. Finding that limit would be equivalent to finding the value of this improper integral. And we call this a type 1 improper integral. So there are two types of improper integrals. A type 1 improper integral is when one of your limits is infinity or negative infinity, or both infinity and negative infinity. That's called an improper integral, a type 1 improper integral. Okay, let me pause for a moment and see if there, please let me know if you have any questions so far. Jonathan?
When you call, you said a type 1 is an improper, it's a type 1 improper integral because one or two of our limits is infinite. Do you mean limits or bounds, or is there a difference in this case?
Well, limit, you know what, I should really, because now you got the limit as t approaches negative infinity. I mean, usually we call the bottom and top numbers, left and right limits on our integral, but let's call them bounds. That's fine, absolutely, absolutely.
Thank you.
If one of our bounds is infinity or negative infinity, we have a type 1 improper integral. All right. And so now look what we got. Our integrand is x times v to the x. You've seen this kind of situation before. You're going to use integration by parts on this. You're going to let u equal x, and dv will equal e to the x dx. Okay, and now integration by parts. So integration by parts, remember, is integral of u dv equals u times v minus the integral of v du. Okay, and so it comes up here. So we got our u times v minus the integral of v du. And of course, I keep the limits. It's from t to 0. I know I'm going to call them limits, and that's fine. I keep those limits, the left and right limits, I'll say, they are from t to 0. And I'm going to take whatever this is here, whatever this is going to be. When I evaluate it, I'm going to take the limit as t approaches negative infinity to find out what the answer is. How many remember taking limits in Calculus 1? Sure, Masume remembers that, and a number of you, Helen and Opiani, sure. So you're just taking a limit, and in Calculus 1, you did take limits as t approaches infinity and negative infinity, but this is just a little bit different, but it's still a limit. So okay, so I'm gonna put in 0 for this part here. Okay, for this part here, I'm going to put in 0 and t, and that's going to get me this here. And then for this part here, this integral, well, the antiderivative of e to the x is e to the x. That gets evaluated at 0 and t. And now I just substitute in the 0 and t on the second part, and that gets me down here. Yes, IB?
What is that straight line? Where you...
Oh, straight, you mean, hold on, this?
Near UV.
This here?
Yes.
That just means evaluate e to the x at 0 and t. It's notation.
All right.
I have my antiderivative now. I want to evaluate it at 0 and t.
Okay. Thank you.
Okay, very good. So I'm down here now. I'm down here. And this is going to be negative t times e to the t minus 1 plus e to the t. That's what we're going to get. And we have to evaluate that limit. So are there any questions before we move to the next page?
So Professor, did you put that 1 in there because anything rise to 0, it's 1?
That's right. I mean, well, e to the 0 is equal to 1, yes. Of course, 0 to the 0 is not defined, but right, that's right. That's right.
Okay.
All right. Well, then let's proceed on. Now we have a limit problem to do. Now we have a limit problem. Franklin, the reason we changed t, we wrote the so this here, this is our improper integral. But all our integration techniques are based on proper integrals, where the left and right limits to the integral are finite numbers. So what I do is I replace that negative infinity there with a t. Think of t as some finite number. And so I'm going to find an expression for this proper integral here. And once I find it, then I'm going to let t go to negative infinity. And then that'll be equivalent to my improper integral. All right, that's what we had to do. And now here we are. We're trying to evaluate this limit. Very good, Franklin. Excellent, excellent. So negative 1, is that affected by the limit at all? That constant, is that affected by the limit as t goes to negative infinity? Should it be affected or not? Well, negative 1 is not a function of t, so that just stays. In other words, that's not going to cause us any problems. Now, e to the t, as t approaches negative infinity, e to the t is going to approach e to the negative infinity, which is like 1 over e to the positive infinity, right? Hold on. Let me do this again. What I'm trying to do is I want to look at these different terms. The negative 1 is good. You don't got to worry about that. E to the t, okay, as t gets large, as t goes to negative infinity, that's going to approach e to the negative infinity, which is like 1 over e to the positive infinity. And what's that equal to? 1 over e to the positive infinity. What would that be equal to? 1 over a very, 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 very big number would basically be equal to closer and closer to 0. Very good, Jonathan. That's right. So there's no problem with that limit. But the first limit, I won't worry about the negative. First limit, the t is going to negative infinity, and e to the t, as t goes to negative infinity, that's going to go to 0. So here you have an indeterminate form. This is indeterminate. Negative infinity, negative infinity times 0. So that means then we need to use L'Hopital's rule to help us. So I'm going to take t times e to the t, okay, and what I can do, I mean, I guess I can put a step in here. I can write this over 1, and then I can multiply the top and the bottom by e to the negative t power. Okay, now e to the t times e to the negative t, this part here, is just e to the t plus negative t, which is e to the 0, which is 1. Okay, so on top you're left with t, and on the bottom you're left then with e to the negative t. So in terms of L'Hopital's rule, this is like function f over function g. And function f goes to negative infinity, and function g, you know, e to the negative t, would approach e to the negative infinity as t goes to negative infinity, which is e to the positive infinity, and that's infinity. So you have an indeterminate form, negative infinity over positive infinity. And you can use L'Hopital's rule on it. Now, what's L'Hopital's rule say? It says, all right, if you have the ratio, the indeterminate form like that, just take the derivative of your numerator function f prime over the derivative of your denominator function g prime. And when you take the limit, you'll get 0. And so now I know what this first expression here, t times e to the tth power, approaches as t approaches negative infinity. Now I know, but I needed L'Hopital's rule to find that out, and that's why we had to cover section 4.5 before section 5.10. Are there any questions up to here?
Can you explain the rule one more time?
Explain the L'Hopital's rule, Mandy.
Mm.
L'Hopital's rule says that if you have an indeterminate form, like 0 divided by 0, or plus or minus infinity over plus or minus infinity, I mean, these are the indeterminate forms that section 4.5 talks about. If you have that kind of situation, meaning that, you know, f over g, if you I want to say this the right way, if you have the limit as x approaches, say, a, of f over g, and these functions f and g both either approach 0 or they both either approach plus or minus infinity, then L'Hopital's rule says that that limit would be equal to this limit as x approaches a of f prime over g prime. That's the L'Hopital's rule from section 4.5. And you actually have your homework assignment for Wednesday deals with L'Hopital's rule. We talked about it last week, but I know you were focused on your section 5.9 homework, but that's what it says. And so this now allows us to find that the limit of that first expression as t approaches negative infinity. And so now, you know, I have a limit of 3 functions. That's the sum of these 3 limits here. And I know, you know, well, I guess I can put a negative here, right? I know the first value, I know the second value, I know the third value. I know it's 0 because I used L'Hopital's rule. I used L'Hopital's rule here to show that that the limit equals 0. I know it because of this. This is how I know. The h here, when I put an h above the equal sign, that means I've applied L'Hopital's rule. So you don't need to use L'Hopital's rule all the time, but it comes up sometimes. Okay, good question, good question. And so you end up getting an integral. This improper integral converges to -1. It converges to -1. And I'll come back to this page, but I want to just show you something. So the area here between the function x times e to the x and that x-axis, all that area is below the x-axis, right? So that area should be negative. We should expect it to be a negative area, but it's finite. That area is finite. Even though the area keeps accumulating, you know, on and on and on, it keeps accumulating. The rate of buildup is slow enough so that the area is finite, and you get -1. And this is used a lot. This is like in differential equations. If you have to take Math 282, when you study Laplace transforms, which is very big in differential equations, you'll be working with improper integrals. All right, are there any other good questions?
Yeah, the problem asked if it converges or diverges. How do we know if it does either one?
All right, good question, Jonathan. Let me go to the next page. So the area is -1, and this is a finite number. It's a finite amount of area. So in that case, we say the integral converges. That's how you know your integral converges. The limit existed, and it's a finite number. So our integral converged. Now, if we took the limit and got like infinity or negative infinity, the integral would diverge. Very good question. Okay. Susanna, if the integral were to converge to 0, if the limit were equal to 0 when we were done, that's convergence also. Yes. If the limit equals any finite number, the integral converges. The improper integral converges.
So, Professor, the only way it can diverge if it's only infinity or minus infinity?
Well, you could have a situation like this. That certainly is right, correct, but I want to be a little bit careful. There are situations where, like, you could have it is. I mean, that's true. That is right, but there is one more case. You could have an integral like this. You could have an integral from, like, say 0 to infinity of the cosine of x dx. That integral, because the cosine wave, you can get an antiderivative, but in the limit, it's never going to settle down to a number. But those are not necessarily, I'm trying to, I mean, that's an example, but generally, I mean, for at least the majority of your homework, if the limit is infinity or negative infinity, the improper integral diverges. And if the improper integral, if the limit of it, if when you compute the limit, if you get a finite number, the improper integral converges. Okay, good questions. So Mandy, Yonatan, and Clea have good questions. Let's look at another problem. Let's look at this one. Let me give you a moment to copy this example down. Okay, so let's see now what this is. This is an improper integral. This is an improper integral. Okay, why? Why? I don't see. I mean, the limits, the left and right limits are finite numbers, 2 and 5. The function, of course, the function here, f of x, is equal to 1 divided by the square root of x minus 2. Why would this be an improper integral? What's making this integral improper? Do you have an idea?
The square root?
Square root's okay. Square root's okay, Clea, Yonatan. Square root's okay. You've
It's
done
the
integrals with square roots before. Mohammed,
it's the 2 in the denominator.
what's the problem with the 2 in the denominator, Mohammed? And Jasmine agrees with you.
It would
What's the
make
problem?
it would make it would make the denominator 0.
That's right. That's right. That's right. And Nihat agrees with you. Yeah, the 2 here would make this denominator 0, and you can't have 1 over the square root of 0. As a matter of fact, for this function, 1 divided by the square root of x minus 2, at x equals 2, what would you have? What would the function do? At x equals 2.
Undefined.
And graphically, undefined, that's right, Jonathan and John. Graphically, what would that mean when you have undefined? Okay, so Jonathan, you're thinking of vertical asymptote, and that's right. That's right. So let's take a look here. Let's take a look at a picture here in our solution. So here is this function, 1 divided by the square root of x minus 2. Well, essentially, John, it's a little more than you got to be a little bit careful on this. I mean, here is the function, square root of x minus 2. Okay, I've drawn it here from 2 to 5. But since the function's not defined at x equals 2, there's an vertical asymptote there. It's like, the tangent function. The tangent function is not defined on like a negative pi over 2 or pi over 2, right? So you have asymptotes at those angles for a graph of the tangent function. It's the same thing here. Same kind of thing. We have an asymptote at x equals 2. Now our integral here, we are trying to find the area bounded between the function 1 over square root of x minus 2 and the x-axis. But because of the asymptote, you're getting an accumulation of area here that goes on and on forever. The question is, what's the rate of the accumulation? Okay, how fast does, how does the area accumulate at a rate at which the area becomes infinite, or slow enough so that the area becomes finite? And that's where, that's what we got to figure out. But so this is what's called a type 2 improper integral. It's a type 2 improper integral.
Professor,
Yes, Clea.
a question. Why do you do the limit t goes to 2 plus?
Oh, why is that? Good question. So when we write our improper integral, we're writing it as a limit again. And I will get to that question just in a moment. The 2 is the problem, right? So we replace the 2 with the t.
Yeah.
Everything else stays the same. And then we take the limit as t approaches 2 from the right. And that's because between 5 and 2, you're not approaching, it's not a two-sided limit. You're not approaching 2 from the left and the right. Since your limits are from 2 to 5, you have to be approaching 2 from the right side. And that's why you have 2 from the right. Good question. Good question. Okay, well now basically, it's like, okay, well, what do we do? Well, simple substitution will work here. Let u equals x minus 2. Then du equals dx. And so now we rewrite our integral with respect to the variable u. So 3, why do we have a 3 there? Well, 5, the top limit is 3. That's because 5 minus 2 equals 3. U equals x minus 2. Our top limit was 5. So 5 minus 2 is 3. And then t would become, the bottom limit, t would become t minus 2. And I'm still taking the limit as t approaches 2 from the right. You notice how I carry that limit in the problem. I don't like do the problem without bringing the limit along, because we have to recognize that an improper integral problem, when you're solving it, you're really solving a limit problem. Okay. So we get down to here. Please let me know if you have any questions. Yes, Jonathan.
Why can't we just say that the bottom integral is, the bottom bound or bottom limit is 0?
Well, because the bottom limit is t. Here, the bottom limit is t. And since u equals that's an x limit, because we're integrating with respect to x in the beginning. Since u equals x minus 2, wouldn't the bottom limit then be t minus 2? And I mean, I understand what you're saying. Well, we're taking the limit as t approaches 2, so t minus 2 will go to 0. But we can't do that yet. We can't take the limit yet. We have to do our integration first before we take the limit.
All right.
Okay? Okay. Order of operation, very good question. Order of operations. Before we take the limit, we have to evaluate this antiderivative, that definite integral, right? All right, are there any other good questions before I go to the next page? Well, the antiderivative of u to the negative half power is 2 times u to the positive half power, right? Because, again, the old trick, add 1, do that, right? And so you got to be a little bit careful here. Hold on. Yeah, that's right. So you get u to the negative a half divided by a half. And that, sorry, u to the positive half divided by half. That's 2 times u to the half. So those antiderivatives are no problem for us anymore. And so, okay, let's keep going. So there's my antiderivative, 2 times u to the half power. And I'm going to substitute in the 3 and the t minus 2. And that's what I do here. And now at this point, I guess I can put an extra step in. I could, now I'm going to take the limit. I'd have 2 times root 3 minus 2 times square root of 2 minus 2. Right? Because now I do what Jonathan wanted to do. Now I'm going to put in the 2. Okay, right there. And so I get 2 root 3 minus 2 times root 0. I get 2 root 3. And that makes perfect sense. I'll just go back to this real quick. The area is positive. The integral converges. And we would expect, if the integral converged, that the area be positive area, because the function is entirely above the x-axis. So we get 2 root 3. Right, I'll just put this in. And so The integral equals 2 root 3, and so this integral converges. So in WebAssign, when you do these kind of problems, you really have to work the integral out to see if the integral converges or diverges first. Usually what happens in WebAssign is that, like for a question, a portion of the problem will be multiple choice. Does the integral converge or diverge? You have one chance to get that right. And then the other portion of the problem will be find that if it converges, find the value. So, but that multiple choice part, you have to be careful on that. So, you know, and they do that because they want you to be sure that you are, you know, not guessing at that. So, yes, Mandy, yes, I will go back a page. Let me go back here. I'll go back to the graph. Yes, let's give just a moment for folks to, let's make sure everybody has this copied, and then we will indeed go back to where that graph is. Are there any questions? Okay. Well, Mandy, let me go back to the graph. So the graph, you can't tell from the graph. You can't tell from the graph if the integral is going to converge or diverge. It depends on the function. It depends on what the function is. And different functions will do different things. The only way you can tell, is to go through the process of finding the limit. It's the only way you can do it. Okay, all right, so you're good, all right. Now what I'd like to do, I'd like to give you a 10-minute break here. We do need to do a few more examples from section 5.10. But if there are no questions, I'll stop the lecture here. Okay, I'll stop the lecture and give you some class time here. Take a little break.